Hello everyone, this is the 10th lecture in real analysis, and in this lecture we're going to discuss inverse functions. So we are going to give a definition of an inverse function, we are going to discuss equivalent definitions, and we are going to provide some examples. Before we proceed further, let us recall what is one-to-one function, what is an on-to function, and what is a bijection. These definitions were given in the previous lecture, lecture 9, and the link to this lecture is provided in the description of this video in case you want to watch it. But we are going to review these definitions here. So let x and y be non-empty sets, and let f from x to y be a function. The function f is one-to-one if for every x1, x2 in capital X, f of x1 equals to f of x2 implies that x1 is equal to x2. So in the previous video we discussed the horizontal line test. So if a horizontal line intersects the graph of a function at more than one point, then that function is not one-to-one. The function f is onto if for every y in capital Y there exists an x in capital X such that f of x is equal to y. That is, if the range of the function f is equal to the codomain y. And finally, the function f is a bijection if f is both one-to-one and onto. So now that we have refreshed our memory about what is one-to-one function, what is onto function, and what is a bijection, let us define an inverse function. So again, let x and y be non-empty sets, and let f from x to y be a function such that it satisfies two conditions. So the first condition is that the range of the function f is equal to y. So that means that f is onto. And the second condition is that for every y in capital Y in the codomain, there exists a unique x in capital X such that f of x is equal to y. So the existence is clear because the range of f is equal to y, the function f is onto. What is important is the uniqueness of this x. So in this case, if these two conditions hold, we say that the function f has an inverse, and we define its inverse function as f inverse from y to x. F inverse of y is equal to x, where x is the unique elements in capital X such that f of x is equal to y. So on a diagram, the situation looks as follows. So we have the set x, we have the set y, we have the function f, that maps the set x to the set y. So if we have a point little x, it is mapped to the point f of x in the set y. And the function f inverse, it maps the set y into the set x, and it maps the point y to the point x. So let us consider this example. Let us look at the function f from r to r given by the formula f of x equals to 2x minus 1. So the graph of this function is just a straight line, and what we want to do is we want to find f inverse. So first of all, we need to verify that f inverse exists. So to verify that f inverse exists, we need to show two conditions by the previous definition, right? So the first condition is that f of r is equal to r, so we want to show that the function f is onto. And the second condition is that whenever we take y in the codomain of the function, there exists a unique x real number such that 2x minus 1 is equal to y. So we are going to show both conditions at the same time. So let y be a real number, then 2x minus 1 is equal to y if and only if 2x is equal to y plus 1, which is true if and only if x is equal to y plus 1 over 2. So what does this show? It shows that r is the range of the function f, so range of the function f is equal to r, so that verifies condition 1. And it shows that for every y in R, there exists a unique x, which is given by this formula, x equals to y plus 1 over 2, such that f of x is equal to y. So for every y in R, there exists a unique x, which is given by the formula y plus 1 over 2, such that f of x is equal to y. So both conditions are satisfied, so the function indeed has an inverse, and actually we already found the inverse. So the inverse function f inverse is a function from R to R, and it's given by the formula f inverse of y is equal to y plus 1 over 2, which we can rewrite as f inverse of x equals to x plus 1 over 2. So the interesting observation here that if we are going to graph the function y equals to x plus 1 over 2, so if we look here on this graph, we can see that the graph of the function, of the inverse function, which is x plus 1 over 2, is the reflection of the graph of the original function 2x plus 1 across the line y equals to x. So this is an interesting observation. So let us now consider the following theorem. It gives us equivalent definitions of the inverse function. So as before, let x and y be non-empty sets and let f be a function from x to y. Then the following statements are equivalent. The first statement is that f has an inverse. The second statement is that f is a bijection. So basically the theorem says that a function f has an inverse if and only if it is a bijection. And the third statement is that there exists a function g from y to x such that for every x in x, g of f of x is equal to x, and for every y in y, f of g of y is equal to y, and then this function g is unique and it is equal to f inverse. This statement I is an equivalent way to state that a function f has an inverse. So we are not going to prove the entire theorem. I'm just going to give you a hint that the best way to prove this theorem is to show that I is equivalent to II, and it follows directly from the definition. So its a proof is very straightforward, and then we can show that II is equivalent to III. So we are going to prove that III implies II. So let us assume the statement III. So let us assume that there exists a function g from y to x such that g of f of x is equal to x for every x in capital X, and f of g of y is equal to y for every y in capital Y. This function g is unique and it is the inverse function of the function f. So we want to show the statement II. So we want to show that f is a bijection. So we want to show that f is 1 to 1 and onto, right? Because to be a bijection, it means to be 1 to 1 and onto. So first of all, let us show that the function f is 1 to 1. So let x1 and x2 be 2 points in x such that f of x1 is equal to f of x2. So we want to show that x1 is equal to x2. So we are going to use our function g. So then g of f of x1 is equal to g of f of x2. However, g of f of x1 by the statement III is equal to x1, and g of f of x2 is equal to x2. So we show that x1 is equal to x2. So f of x1 equals to f of x2 implies that x1 is equal to x2, so that means that the function f is 1 to 1. So the next thing that we want to show is that the function f is on 2. So let y be a point in the set capital Y. So let us consider x equals to g of y. So we have that f of x is equal to f of g of y, which is equal to y by the statement I. So for this y in capital Y, there exists an x in capital X such that f of x is equal to y. So that proves that the function f is on 2. So f is on 2. So in summary, we proved that f is 1 to 1 and on 2, so then it is a bijection, and that finishes our proof of the implication I implies II. So QED. So we are going to finish with this example. We want to verify that the function g of x equals to x plus 2 over 3 is the inverse of the function f of x, which is given by the formula 3x minus 2. So let us note that g is a function defined on the set of all real numbers, and it acts into the set of real numbers, and f is a function, also a function from R to R. So let us compute g of f of x. So for every x real number, g of f of x it's going to be g of 3x minus 2, which is 3x minus 2 plus 2 over 3, which is 3x over 3, which is equal to x. And f of g of x is f of x plus 2 over 3, which is 3 times x plus 2 over 3 minus 2, which is x plus 2 minus 2, which is equal to x. So we have that g of f of x is equal to x, g of f of x is equal to x, and f of g of x is equal to x. So then by the statement I of the previous theorem, g is the inverse function of the function f, QED. This is all for this video. Thank you for watching it. Please put a like underneath this video if you liked it. Please subscribe to this channel, support this work, and be good at math.